So here we discuss the super heterodyne receivers. These receivers are generally used for both the broadcast AM and FM systems. So they consist of an RF stage and a radio frequency section. Then it is followed by a frequency converter. Then frequency converter is followed by an intermediate frequency amplifier. After that we have an envelope detector to detect the signal, and then after envelope detector the signal is converted into an audio signal, so we need an audio amplifier as well. So the RF section, this one consists of simply a tunable filter and an amplifier. So it picks up the desired station by tuning the filter to the right frequency band. The next section, which is the frequency mixer section, it basically converts the carrier frequency. So for example, this is the FM signal or AM signal frequency that is at the input. The frequency mixer converts that into the IF frequency, so omega IF, the intermediate frequency. So the complete structure of this super heterodyne receiver is shown here. So here we have an antenna, this one. Then we have the RF stage, which consists of a tunable band pass filter, which tunes the RF amplifier and the band pass filter to this particular frequency that is at the input, the particular channel that we want to choose. So then we have the frequency mixer. Frequency mixer converts the signal into an intermediate frequency, which is amplified by the RF amplifier. We have an envelope detector, and then we have an audio amplifier. So let's discuss each of these blocks separately. Now, before that, the down conversion that takes place at the intermediate frequency stage is through this expression. So we have a local oscillator at the down conversion stage whose frequency is tuned to the input channel frequency plus a fixed IF frequency, FIF. So the local oscillator and the RF tunable filter at the beginning, they are combined, they are simultaneously tuned through one joint knob. So as we increase the, let's say, the RF tunable frequency, we have to add FIF to it. So similarly, the knob that increases this RF tunable frequency also increases the frequency of the intermediate local oscillator that is at the intermediate stage. So the difference between the local oscillator frequency and the carrier frequency always remains equal to FIF, right? So this super heterodyne structure is broadly utilized in most broadcast systems. So the intermediate frequency that are generally used are 455 kilohertz for AM radio. For FM radio, it's 10.7 megahertz, and for TV reception, it's 38 megahertz. So the translation of all stations to a fixed intermediate frequency allows us to obtain adequate selectivity. So when we tune all the stations to this fixed intermediate frequency, the stages or the amplifiers and filters that follow after this point, they need to be tuned to a single IF frequency. So that allows more selectivity, improved selectivity of the signal, because it is difficult to design precise band pass filters of 10 kilohertz. So which is the modulated audio spectrum. Generally it occupies 10 kilohertz. So if the frequency is high, if we use carrier frequency inside for processing, then it becomes very difficult to, because this carrier frequency is quite high, then it becomes difficult to design band pass filters that have a bandwidth of 10 kilohertz only, because compared to the carrier frequency, this bandwidth is quite small. So the filter selectivity needs to be very good, which is quite difficult to design. So that's why we convert this carrier frequency, the channel frequency, to these IF frequencies. So RF filter cannot provide adequate selectivity against adjacent channels. So that's why, as I mentioned, we use IF frequencies. So the signal that is translated to IF frequency is further amplified by an IF amplifier. So as you can see, after this stage is when the signal is converted to IF frequency, all the remaining stages needs to be tuned to a single IF frequency. So they can be just hard wired to this frequency. We don't need to have tunable components after the IF stage. So because the IF frequency is reasonably low, moreover its center frequency is fixed and factory tuned. So this is the main the benefit. So because of these features, we get more selectivity at the later stages. So the IF section can effectively suppress adjacent channel interference because of its high selectivity. So since the selectivity is high, so the adjacent channel interference is suppressed quite effectively. And then after that we have the envelope detection stage, which detects the audio signal that was used to modulate the carrier signal. So the entire selectivity is practically realized in the IF section. The RF section plays a negligible role. So the selectivity is performed mainly in the IF section. Main function of the RF section is just to reject the image frequency. So we'll discuss in the coming slides what is an image frequency, but this is the main purpose of the RF section, that is at the input. So now image frequency is discussed here. So let's say output of the mixer or converter consists of the components that is the difference between the carrier and the local oscillator. So at the output of the mixer we get this signal, so which is the FIF, the IF signal. It's the difference between the carrier and the local oscillator. Now we can have a situation where the carrier is, let's say, 1000 kilohertz. The local oscillator, in this case, if the signal is, let's assume it's an AM signal, so the IF needs to be constant. So the local oscillator would then be tuned at 1455 kilohertz. Now let's say we have another carrier that is at a frequency of 1910 kilohertz. So at this point, for this frequency, the local oscillator would be tuned to 1455 kilohertz, because 1455 plus 455 of the constant IF frequency, when you add them up we get 1910 kilohertz. So if we have a signal at the input having this frequency, so then the IF would again be 455 kilohertz, and so this signal will also move to the next stage, that is the stages that follow the IF conversion, down conversion stage. So that's why we would be picking two channels that are at very different frequencies. So these two channels are called the image channels. So the channel at 1910 kilohertz, which is the undesired one, is the image of the 1000 kilohertz channel. So that's why the RF stage, because these two frequencies are at very different values, so the RF stage can easily filter this one out. So that is the main purpose of the RF stage that we have at the input of the receiver. Now AM stations that are FIF, that have an FIF of 910 kilohertz apart, are called image stations, and both would appear simultaneously at the IF output in the absence of the RF filter and receiver. So all the AM channels that have a frequency difference of 910 kilohertz, they will all appear at the they are called the image stations, and they will appear at the IF output. So finally, we now discuss why this particular design is used for the receiver. Now, since local oscillator FLO is higher than the incoming carrier frequency, the receiver is called a super heterodyne receiver. This is the main reason for calling it a super heterodyne. If we choose FLO higher than the FC, the incoming carrier frequency, the tuning ratio of the maximum to minimum frequency for the local oscillator becomes small. The AM broadcast band frequencies, they generally range between these values 530 to 710 kilohertz. Now the super heterodyne FLO would range between these two values 985 to 2165 kilohertz. That is, how do we get this range? We add 455 the IF frequency to these bands, and so we will get these values. Now the ratio between the maximum, which is 2165, to the minimum 985 is in this case 2.197. so if we had used a subheterodyne range, so in that case, which would mean that the local oscillator has a lower frequency than the carrier, in that case the minimum frequency of local oscillator would be 75 kilohertz and the maximum would be 1255 kilohertz. So if we find out the ratio between the maximum value and the minimum value, that would be a large value of 16.73. so that means if we use subheterodyne receivers, the tuning range required for the local oscillator would be very large. So that is why it's not generally desired. So this completes the discussion on the super heterodyne receivers.